Okay, YouTube, in this video we're going to provide an extended explanation of some measures of variation, namely the range, the variance, and the standard deviation for given sets of data. And so in this video I'm really aiming to kind of explain what it is that you're finding when you talk about measures of variation here, notably the variance and standard deviation. And in the next video that you watch with me that follows this one, we'll just use a shortcut formula in order to do the calculations. So let's go ahead and take a look at our thought experiment here. But it says a testing lab wishes to test 2 experimental brands of outdoor paint to see how long each will last before fading. So it says the testing lab, what they do is they make 6 gallons of each type of paint to test. And it says since different chemical agents are added to each group and only 6 cans are involved, these 2 groups constitute 2 small populations. That is, these are the only cans that have ever been created in this way. So they are the entire population of those types of cans ever made. Okay, so we're going to assume that we're dealing with a population here. And I say the results are listed in months are shown below. So we have brand A and brand B. So I guess what you're seeing here is this: if you were to walk into a store and I say, okay, well, we've been, testing brands A and B of paint here, and they're experimental, what type of paint would I, prefer to go with? And that's something I'll ask you to think about here. If these represent the number of months that it'll last before, fading, I get a lot of students, a lot of times they say, well, I'll go with brand A. And the reason why they say this is because, you had one of the cans last 60 months before fading. Whereas, I would say, well, you got to be careful. What if you got stuck with a 10 here? As a matter of fact, what we're really going to do is we're going to look at the spread of this data. And you'll notice that brand A here is very spread apart, whereas brand B is not as spread apart, but it is really what I would say consistently packed, okay? It's like a little crowd here. So I would go with brand B because I could see that there's consistent performance, whereas in brand A, it's kind of spread all over the place. So what we're going to do is this: we're going to find the mean or the average of each of these groups. And so in terms of finding the mean, this is really important that we take our time when doing this. And all I mean is essentially this: remember, when you calculate the mean, what we need to do is we need to sum up all of the data. So since we're talking about a population, we are going to use a capital X to represent our data values, but we're going to find sigma X, that is the sum of all of these data right here. And so if I were to get out my calculator here and I say, okay, so well, 10 plus 60 is 70, plus 50, plus 30, plus 40, plus 20. You'll notice that these sum up to 210 total months. And then underneath this, we say, well, how many total data were there? So we say N. And then you notice I'm using a capital N because we're talking about an entire population here. So we say N is 6 cans of paint. So if we want to find the average for brand A, you notice that I'm going to use a lowercase Greek letter mu, and I'll use a little subscript A to indicate that we're talking about brand A of paint here. But we use mu because we're talking about the mean for an entire population. Remember, we use Greek letters for parameters or population statistics. But we get this: we say 210 months split 6 ways, and according to the calculator, if we were to take that 210 and divide it by 6, we end up with 35. So what we could say here is this: 35, and we ought to label this, and I just don't have a lot of room. We say 35 months. So on average, we say this basically means that the most typical case is that a brand of paint, a can of brand A will last 35 months before it fades. Now looking at brand B here, if we were to sum up all of these values, let's go ahead and find its average here. So sigma X, or the sum of all of our data, would be 35 plus 45 plus 30 plus 35 plus 40 plus 25. And what do you know? It also sums to 210. So one thing I think we should be really clear on here is this. This is 210. We have 6 total data. And so the mean value, or the mean amount of time it'll last before fading for brand B would be 210 6 ways, which is exactly, in this case, exactly 35 months. So when I ask this question, I say, what do the mean values imply about the durability of each brand of paint? Essentially, they, on average, or typically, last the same amount. Typically last the same amount of time. And as I'm writing this, I want you to consider this. Just because they have the same average value, does that necessarily mean that they are perfectly equal? And so the thing that we're basically pointing out here is this: just because you have the same average value doesn't mean you perform the same way. That is, if you were to look at how brand A is spread apart, things are very far spread apart from the average, which is 35 here, whereas 35 centrally located over here, things are very close to the average. So can we come up with a way in this video to essentially describe the spread of the data? And that's what we're going to do, okay? Before we do this, what I want to do is I actually want to put these on the number line, and actually what we'll do is we'll put the average right smack dab in the middle. So what we'll do is we'll call this brand A. I want to represent this visually. You know, I'm a visual person. We have brand B. But essentially what we could do is this. And actually maybe that's not the average. Maybe I notice that brand A goes from 10 up to 60 here. So maybe I'll say that this is you know, 10, 20, 30, 40, 50, and 60. And we'll label these two number lines. I want to label them exactly the same way here. So 40, 50, 60, so that we can compare them straight up. So we say, all right, 30, 40, 50, and 60. So what this is going to allow us to do is not a histogram, okay, but it's kind of a pictograph here where we can represent our cans of paint. All I'm saying is this, since 10 was one of our data in the first one, we say, well, there's a can here, 10. There's a can at 60 also. There's a can at 50. We say a can at 30. A can at 40, and a can at 20. So when we indicate the average here, which I'm going to put on the number line, and I think you should too, we say this is the average of brand A, and we'll even write that it equals 35. Okay. So you know, it makes reasonable sense that it'd be perfectly right here in the middle, that the average value would be there because it's centrally located. It's a measure of central tendency. And likewise with brand B here, we say 35. Well, 35 months would be here. 45 months would be here. 30 months is going to be right here. 30, 35 again. So we're going to have to stack that one. 35. We had a 40, and we also had a 25 monther. So you'll notice, you know, again, we'll put the average on here. We say mu of set B, data set B, which was 35 months. Centrally located. You can see already, obviously, data set A is more spread apart from the average than brand B. So what we're going to be doing is comparing it to the average. So I say in order to better analyze a set of data, we're going to need to look more closely at how the data are quote-unquote spread or how they quote-unquote vary. Okay, so in order to do so, we have three measures of variation. There are only three that we use typically, but these are the range, the variance, and standard deviation. And again, I just want to remind everybody, the range is just the maximum value minus the minimum value. So say, for instance, here, I say the salaries of staff at XYZ manufacturing company are shown below. Let's find the range. Notice that the owner makes 100 grand. It looks like the smallest one here, one of the workers, makes 15 grand. So we say the range, we just use capital R. And we can say 100,000 minus 15,000 leaves us with an 85,000, and this is in dollars. We should label this here, dollar range. So that's a huge range. And when I say that that really represents this entire set of data, the only reason I bring up this set of data here is that the owner, if you were to just take the owner out of this set of data, this would have been $40,000 minus the 15,000 here. Okay, sorry, I should have listed that under here. We say it would have been 40,000 minus 15,000. And the only reason I bring this up is because we say that it is a very, very, you know, like it's a statistic that can be swayed by very large or very small values, the range here. This would bring it all the way back down to $25,000 range, which would be more consistently packed. So just because the range is a good measure of variation, or is a measure of variation, it's not always the best because of large or small data values. So if we were to calculate the range for brand A here, let's go ahead and do this here. We say the range for brand A. The range for brand A would have been 60 minus 10, 50, and this is 50 months. We should always label this. And we say the range for brand B obviously is a lot more packed together. We say it would have been 45 minus 25, which is 20 months. And so instantly I can tell you, oh, okay, well, you know, the range for brand A is like two and a half times as wide as the range for brand B. So range, it'll give you a good measure of how your data is spread. Obviously, we say range on the number line would be the distance from the max to the min here. Okay, so visually we can determine this by looking at the range. What I want to do now is actually calculate the standard deviation for the first time. And you hear this term a lot in statistics, standard deviation, standard deviation. Standard is kind of like, you know, something that is normal. And to deviate means to move away from, okay? So when we calculate the standard deviation, what we're basically going to be doing is this, and I'll just come out and say it. The measure of standard deviation, standard, you know, deviation. If I had to give it like an English translation here, like just paraphrase it, it is the average spread of data from the mean. And you have to understand that the mean is the average. So we say it's the average spread of data from the average. So when you look at this up here, what we're going to be doing is basically this. We're going to find out how far each individual datum is from this central average. And then what we're going to do is we're going to average those distances together. Okay. So essentially what you can see here is, like I'd say 30. Where is it in relation to 35? Here's what I'm actually going to write. It is 5 below it. Whereas 40 was 5 above the mean here. And I can actually do this for all of my data. Say, how far are they from the mean? 50 is 15 above average. I can say from here out to 60, this is 25 above average. And again, going the other way, we say from here to here is negative 15. If you lasted 20 months, you're 15 months below average. And if I went all the way up here, kind of overlapping here, we say 25 months below average here. So when we calculate standard deviation, what we really want to do is take all these distances and average them out. And we know how to find an average. It's very easy to do. We're just going to add all 6 of these distances together and divide by 6. That'll be the average distance of one given data, a typical datum, from this centrally located mean. So what we're going to do is we say find the mean first. And as a matter of fact, we already did find the mean. We're going to do the standard deviation for only brand A here. So we say the brand A mean was 35 months. Now, what we're going to do is this. This is really important. It says find the difference between the mean and the individual data values, or the x values. That is, we're going to subtract the mean from each data value. And this is very important because what this means is, and you should write this down, we're going to take the datum and we're going to subtract the average off of that. It is always the average away from the mean. So we have our data points here. I have my 10, 60, 50, 30, 40, and 20. What we're going to do is we're going to say 10, 60, 50, 30, 40, and 20. And from each of these, we are going to take off the value of the mean. So minus 35, minus 35, minus 35, minus 35, minus 35, minus 35. And what this is it's giving us all of those distances that we just validated visually on that other page. That is, these distances right here. And we're just finding them numerically, okay? So 10 minus 35, this actually means that it's 25 and it's negative. So first thing I want to tell you is this. It means that this data must fall below average if it is negative steps away from it. Likewise, 60 was 25 steps above. Well, then 60 minus 35 is a positive 25. So positive 25, 50 minus 35 is a 15, positive 15. 30 minus 35 is a negative 5. That's how far it is from the mean. We say 40 minus 35 is 5, of course. And then last but not least, 20 minus 35 is a negative 15. So once we have all these distances, recall that what we want to do is we want to find the average distance back to the average. So one thing I want you to do, I would encourage you to do, is this. If you were to add up all 6 of these numbers and divide by however many there are, I hope you notice this here. If you added all these up, the negative 5, positive 5 would cancel. Negative 15 and positive 15 would cancel. Negative 25 and positive 25 would cancel. So if you tried to average all of these distances right now, what you're going to find, we sum up all of these distances that we found here, sum them all up and divide by however many there were. You're going to get 0 over 6, which is 0, which we know better. It is not all data located 0 steps away from the mean. It was more than this, obviously, looking at that. So the reason why this happens is because of the definition of average. Since average is this balancing point, it is this, you could call it the center of the data, kind of the centroid. Then by definition, every time you find all of these distances and add them up and try to average them, you're going to get 0. Okay. So to remedy this, what we actually do is we take all of these results that we have right here and we square them. And what I want everybody to write next to square the result is this. We took the data values minus the mean and we squared them. And the reason why we're going to square them is because what that does is automatically that's going to convert these back to positive numbers for us here. So for instance, when I take negative 25, I say 25 negative and I square it, I get 625. So we say if I square all of these, I get 625. 25 squared is also 625. 15 squared is 225, by the way, sorry. Negative 5 and positive 5 squared, those are both 25. And last but not least, the negative 15 squared gives us the same thing as positive 15 squared, so we get these. What we're going to do now is we're actually going to average these. So when I say add or sum these differences of squares or squared differences, symbolically we could say then what we're doing is we're summing all of these distances that we squared. And so essentially when I add all of these up, what we're going to do is we won't get a negative number this time or a 0, we'll get a positive number. So we get 625 plus 625 plus 225 plus 25 plus 25 plus 225. And so we get 1750. So the sum of all of these comes out to be 1750. Now, since I added up all 6 of these squared distances, we can actually average the squared distance back to the mean. So we're going to divide this sum by n to get the variance. So essentially, here's what I want to start off by saying. We now have done this. We found how far each thing was from the mean, x minus mu. We squared those and we added all this up and we're dividing by however many there were, which is n. And what I'm doing is I'm calling this the variance. Okay. So the variance. We'll talk about what the variance is here in just a moment, but we use a symbol to represent variance, and this is lowercase o with a tail on this side, and this is a lowercase sigma. And you'll notice I wrote sigma squared. this is the variance, okay? So something I want to tell you about the variance, what is it telling me? It does not tell us the average distance that, a typical datum is from this mean. It tells us the average squared distance from the mean. And the reason why we did squared numbers was to bring these back positive again, okay? So we say that the variance, what is variance? It is the average squared distance. We'll hyphenate that there as a single thought adjectives. Squared distance from the mean, okay? We want to know the spread. So in this case, what we got was 1750. And we're dividing this by 6, and we're going to get a number here, 1750 divided by 6. 1750 divided by 6 comes out to be 291.66 repeating, okay? So I'm going to write equals 291, and I'm adamant about this. We're going to keep this as an exact value, repeating. But we say this is how many squared months something was away from the mean on average. What we're going to do is, since now I don't want squared stuff, what I want to do is I want to take the square root of this. So you'll notice it says take the square root of the variance to get the standard deviation. So we say that the variance was given by sigma squared. We are going to take the square root of this to get the standard deviation, which means, well, the square root of anything squared would be just that thing. So this thing right here, this is the symbol for standard deviation. It's a Greek letter, so it's a standard deviation of a population. And so we're going to get the square root of 291.6 repeating. And we can just get the calculator back out and say the square root of this number, boom, is 17.08-ish. So 17, I'm going to say 17.1. Okay, so approximately 17.08 months. Okay, so when I ask, what does a high or low variance suggest about the data? Well, a variance was the average squared distance. And what I want everybody to know is this. When you take everything's distance from the average and you square it, it can get very big very quickly. And when you average a bunch of very big numbers, then what you'll notice is you get a big average, like this one down here. So what I can say is a large variance. Large variance basically means this. My data is very spread. Large variance means very spread. And when you say very spread, you say very spread from what? We say from the mean. Okay? So a small variance, and I'm going to assume you know I mean from the mean here, but basically small variance means a small spread, low spread, okay, of our data. Data is really packed around the average, kind of like brand B. So by definition, we say the variance is the average of the squares of the distances of each value from the mean. And the symbol for population variance is going to be the sigma squared. Okay, so sigma squared is our variance. You'll notice it says find the distance between all the values and the mean, square those, add them all up, and divide by n. So this is our formula here where x are the individual data values, mu is the population mean, and n is the size of the population, number of things in the data. So the standard deviation, when we define this is my favorite part, the standard deviation is like this. It is the average data, average data spread. You know, how on average how far data is spread from the average. So we say the symbol for this is lowercase sigma, and it's just the square root of the variance. So when I give you the definition of standard deviation here, you'll notice that I just took the square root of this formula that you saw here. So what I want to do now is I want to pop back over to our original data set, and we say look at this number line. We say 35. If you were to add 17 onto 35, you would land, let's see here, 35 plus 17 be about 52. So we say, you know, this is approximately positive 17 away from the mean. If we go negative 17 away from the mean, 35 minus 17, you land at about 18 here. You know, we say there, negative 17. But what this number is the standard deviation, but it's also saying, you know, most data on average lie within about 17 steps above or below 35, or about 17 months above or below 35 months. So we are going to do this again. We're going to do it for brand B, but I'm going to do it a little bit more quickly this time. Again, the mean is what we need to calculate first, and we said the mean of brand B was 35. So if we took 35 minus 35, we would get 0. 45, which is our datum minus the mean, is 10, so that must be 10 months above average. 30 minus 35 gives us negative 5, so 5 months below average, that datum. 35 minus 35, of course, is 0. Start thinking about this next one here, 40. That's 5 months above the average, so we get a positive 5 here. And then we say 25 months, well, that's below average. That's 10 months below average. So what we're going to do is we're going to take all of these numbers this time, and you'll notice that our data is much closer to the average for set B, which means when we square these, we're not going to get as big a number. 0 squared is 0. 10 squared is 100. 5 squared, negative 5 squared, that is 25, so we get 0 squared, 5 squared, and then negative 10 squared. So when we sum these this time, we're going to sum up this entire column of squared distances here. And what I get is 100 plus 100 is 200 plus 225 is 250. So much lower this time. And what we'll do is we'll divide this by n. So in this case, we divide this by 6. And what we're going to get is this population variance. But essentially 250, let's do this here. We say 250 divided by 6 gives us about 41 and 2/3. So we say 41.66 repeating, I want that repeater on there, is our variance. And I want to label this. And if you said, what's the variance? It's the average distance something is squared from the mean, squared distance from the mean. So if we want just the standard deviation now, we're going to say stand-dev. Okay, then it's just sigma, and it is by definition the square root of what we just found right here. So we're going to get an approximate value. And so we say the square root of this number here, we'll take the square root of it, we get about 6.45-ish, okay? So 6.45, and we should label this is in months. Okay. So what is this telling me? Well, what it tells me, again, if we pop back over to the original picture here, we say looking at 35, which is centrally located, it's right here. If you were to go about 6.5 months above this, so about 41 months is where you would be. So we would say about 6.5 above. 41.5 is where it would kind of land here. And then we say if we went 6.5 months below 35, this would be 28.5. Is where you would kind of be at in terms of months. You're right there. We're saying that most data lies on average within 6.5 months below or above the average. Okay. So last but not least, when we leave off here, I want to mention this. We say the rounding rule for the standard deviation. It says the final standard deviation value should go out one more decimal place value than that of the original data. So for instance, when I look at my original data here, you'll notice that at most our data went out to, the nearest whole month. So when I reported my standard deviations, I actually went a little bit too far. Standard deviation in this first case, right here, up here, was 17.08 months. We said this should probably be called about 17.1 months. And also on this last page, when we found the standard deviation was about 6.45 months, we might as well just call this about 6.5 months. Okay, and the only reason why is because I want to go out one place value after the holes. So in the next video, we use a very much quicker, shortcut formula to find the standard deviation after we find the variance. Cheers.